if I have a charge and this particle has a positive charge and it's going into this direction with a velocity v, the magnetic field would be pointing into the page this way, a uniform magnetic field. So if I am to adopt the following coordinates, which is basically I have here, this is as x, this is as also z, then in this case, y would be pointing into the page. And I would like to, calculate the direction of the magnetic force. We know that the magnetic force in this case would be given as Q V cross B. So I am using a positive charge. Then in this case, if I am to draw the right hand, in this case, my right hand will be moving or would be curving from V vector toward entering the page. So if I am now just to draw a 3D sketch of the V and the B as a 3D, not within this coordinate, however, within a different coordinate, just to show you. So this one is V, and this one is B. In this case, this coordinate will be a bit also twisted, just to show you the coordinate in this case with a 3D. This is going to be X, this is going to be Y, and this one is going to be the Z, just to show you what's going to happen. In this case, I will be going as again from the vector V toward the B. So if I am to draw the right hand here, I will be drawing it like this, where those are the fingers, and in this case, my thumb is going to be pointing up like this. So my direction would be along the positive z-axis, and in this case, if I am to take the again magnetic force, FB will be Q V times B. Here the angle is theta is 90 degrees, that's why sine theta is 1, and then the direction would be k hat. So this is the direction. If I am to enhance the picture here, just trying to make it as a 3D as well. So we'll start with the thumb. This is the thumb, and then like this. So here I'm going from the vector V toward the vector B. So this is how we do it for the positive charge. For the negative charge, you start with the right hand, and then whatever direction you get, you flip it, or you can do the left hand, use your left hand to find the correct direction. So in this case, if I assume I have a negative charge that is also going in this direction with a magnetic field that is also pointing into the page. In this case, if I am to use the left hand to find the exact direction of the magnetic force, then I can, as I said, go. Let me do this one in 3D. So if X is, if this is X, this is Y, and this is Z, then in this case, I have the velocity going along the X. I have the magnetic field going into this direction. Then using the left hand going from V, curving from V toward B, you will notice that your thumb will be pointing downward. In this case, if I am again to try to draw this with the left hand, then in this case your thumb is pointing downward like this, and in this case FB would be Q V B, and the direction is minus K hat. So this is how we do it for the positive charge and for the negative charge as well. Now let's move on now to the current, the case with the current. In this case, we know that the magnetic force is defined by I L cross B. Let me start first with the wire case. So if I have a wire, this wire has current going into it, and my coordinates again are X, Z, Y. Then what's going to happen here, using the right hand rule, I will use my thumb for the direction of the current, and my fingers that are curving, I will use them to define the direction of the magnetic field. And as you will see here, we will have two regions with distinguished magnetic field direction. Using the right hand rule, if I am to draw now my right hand, and remember I use the right hand rule whenever I have the current that is assumed to be going in the direction of the positive charges. So if the current is going this way, I will be using my right hand rule. My thumb here will be defining the direction of the current, and then my fingers that are curving will define the direction of the magnetic field. So in this case, as you can see, for the lower part, for the region below the wire, I have the magnetic field entering into the page, as you can see here. And the region above the wire, I have the current leaving or going out of the page. So this is the direction of the magnetic field out of the page. However, below the wire will be into the page. So this is what's going to happen if this is how the magnetic field is going to uh, behave when my current is going into the straight wire. And again, I said for the case of the straight wire, we use the thumb as the direction for the current, and then we let the fingers that can curve define the direction of the magnetic field. Now, this is again for the straight wire. What happens if my wire was into turns, like the case for the coil or the case for the solenoid? In this case, in this case, if I have a loop that has a current basically rotating into this loop. So if this is the direction of the current, in this case, since the current is the one that rotating this way, I will use my fingers for the current. So let me define my coordinates again. So this is going to be my x, this is going to be my z, and entering into the page is my y. So in this case, if I am to use my right hand rule to define the direction of the magnetic field, I will draw my fingers such that my fingers are taking the directions of the current, and in this case, my thumb will be pointing into the page. So this is going to be now my thumb. This is going to be my thumb. So this is my thumb. It will be pointing into the screen, into the page. So in this case, I can draw my magnetic field. Again, here I have two regions. My first region is within this loop. Again, the magnetic field will be going into the page. So this is going to be my magnetic field pointing into the page. However, the magnetic field outside the loop will be pointing out of the page. So always remember, between the wire itself defines two directions of magnetic field. So here it will be the one that is outside the loop is out of the page. The one that is inside the loop will be into the page. And my right hand rule here basically defines the direction of the magnetic field into the loop, the direction of the magnetic field into the loop. Now, just to understand what you can do for the case of the wire, if you use your thumb for the current, so let's take this piece for example, and this piece here of that wire, you can still treat it as if it's a straight line, and you can see that the magnetic field is based on this. It will be pointing out of the page on the up above the wire and pointing into the page below the wire, and this is what's happening right here in this region. Right here in this region, if I cut this region, you will see that it is giving me the same as what I have explained there. For assuming that this piece of wire is straight enough, I can use my thumb for the direction of the current, and then the magnetic field, as you can see, below the wire is entering into the page, above the wire is pointing out of the page. So this is basically the cases that you can use the right hand rule on. Also, one other case that we can mention is the solenoid. Again, for the case of the solenoid, assume that this is the cross section of the solenoid. If you want to calculate or know the direction of the current basically, or the magnetic field. So for this case, if you've been given the direction of the magnetic field to be pointing in this direction, and you've been asked to calculate the direction of the current, for example in this wire, then you can use the right hand rule. Now we will use our thumb as the direction of this straight, as we can see, magnetic field. So if I am to use my thumb here as the magnetic field for the right hand rule, then in this case you will see that your finger is, let me draw this one in a better position. The direction of the magnetic field will be like this. Is those are the fingers, and this is the thumb. And as you can see here, the magnetic field will be entering into the page and the upper ones and leaving out of the page on the lower cross section. So this is how the current is going to, so this is the direction of the current, this is how the current is going to go and the solenoid.